Hello, good morning, everybody. Welcome. Before we begin, we need to decide about the final term. Theoretically, there was an idea from your leader, so Julia Rzepka, so to move the midterm, the final term, to 15th, if I'm not mistaken. Yeah, 15th, 15th June. So 15th is so in 2 weeks, almost in 2 weeks, because 2 dates were proposed, so 14th and 15th at 1:15. Yeah, I didn't get a response because I suggested 15th, so Wednesday at 1:15. I didn't get. Oh, here's Julia. Julia, my question already. Is 15th June okay for the final?
Yes, I think so. I asked on the group and nobody said this is not okay, so I think it's fine.
Good. Okay, that's fine then. So that's agreed. So 15th at 15th June at 1:15. I will give you the room next week. Probably it's going to be 201, but maybe some other one. So we will see. We will see. So I will give you an info from Jesus and on the portal. Next question. Next question before we begin. Because you have a chance to elect, you had a chance to elect Artos. So in your course of study, did you have the Artos course? This semester or previous one? Because if I'm not mistaken.
Yes, we have it this semester.
You have it this semester. Good. Good. So then that's good. So then we don't take this subject, and then we go to our final 2 lectures. Our final 2 lectures, we move back. In case of embedded systems, we can build an embedded system on a microcontroller. We can build it using a digital signal controller. We can build it around the DSP, although DSP it's actually DSC today, so the pure DSPs are not really very often used inside embedded systems, as they are rather used inside larger constructions, inside kind of calculation modules. But for the embedded systems, you usually use DSCs, microcontrollers, and of course we are using the third leg. We have the third option we have to build embedded systems around. It's a programmable logic. We did talk about the programmable logic during the ITM course with the where the programmable logic was for us a kind of an integration or simplification of the construction of basic logic circuits. So we talked about the PLA, PAL, PLD, CPLD. So this kind of simple programmable elements. Those kind of programmable logic, simple ones. Today we have sometimes in microcontrollers available as a separate peripheral block in a microcontroller. The peripheral block that is to be used as a glue logic to the glue logic between the microcontroller and some digital components and some digital sensors. So for this kind of operations, but that's the simple logic. That's the simple programmable logic. As I tried to tell you a year ago. So during ITM course, the programmable logic can be much more sophisticated and much more complex. And today I will try today, and next week we'll try to get into this subject deeper, but from the perspective of the device which is delivering more than a microcontroller, which is delivering more and at higher speed solutions, and then we can get with the microcontroller, classic microcontroller, or a digital signal controller. So we'll take a look from this perspective on programmable logic, and I will try to remind you. So unfortunately, we don't have enough time to get this subject into during laboratory, but we'll try to show you some applications, some simulations, how it works in case of programmable logic, how we develop our software in programmable logic. So unfortunately, we don't have time for it during laboratory, so we have to do it today and next week during our two final lectures. So we'll talk about that's the plan. So first the theory, a bit review of the FPGA structure of the complex FPGAs, and then some examples of software development and software development in hardware description language. Why programmable logic? That's the question. That's always a tricky question in reality. So the basic features for microcontrollers, and against it you have on the slide. So they are just a couple of. So I always have a problem with answering this question. So which is better and when? So theoretically, microcontrollers are easy to program, excellent for control and state machine applications. So here, the most important part is the easy here, the easy word. Why is it easy to program? So yeah, you could argue with this, saying, oh, we did have to work in assembly and the assembly is horrible. So it was your nightmare or something like this previous semester. Maybe it was, but unfortunately, FPGA is a bit worse. Why is it a bit worse? A bit, not really a bit. As we mentioned during the ITM course, the FPGAs are kind of evolution from simple connection of logic elements. Couple of blocks were added, a couple of improvements were made from this very trivial PAL or PLA programmable planes, programmable chips. Yet the ground, the base is still the same, which means that we have to focus very much on the hardware still. So even if we are talking about programming on the system level, even if we try to use a System C or similar programming language which resembles high-level languages, but in case of programmable logic, it's not possible to obtain a success without thinking hardware, without having a hardware construction at your back, without knowing the essence of logic. So it's, in my opinion, in case of microcontrollers, you can try just to write high-level instructions and use high-level languages. You can try to use a Python. It's not going to be very efficient, but still it's going to work here using this kind of. So there is no Python here, but there are some languages that facilitate the code creation in case of FPGAs. But it all ends up in the hardware. So there's really no way around. So there are no shortcuts here, and that makes, because we need to play with hardware, then we need, in fact, in case of embedded systems, in case of FPGAs in the embedded systems, not only we need to think about the algorithms and about integrating all the sensors and the human-machine interface and whatever we need in our application in case of FPGA, but also, unfortunately, we must think about such basic things like signal propagation or clock jitter or clock skew. So we need to get down to this level. to careful planning of pinouts. So in microcontrollers, of course, we need to play with pinout a bit, but we don't care about it. So we have a clocking, we pay the price for the clock subsystem, for the peripherals, and we get what we pay for. We are just to use it. In case of FPGA, it's not that simple. In case of microcontroller, another positive thing about microcontroller, and of course negative for the FPGAs, is that the resources remain fairly constant with the increasing complexity. What doesn't remain constant is the execution time. So imagine a situations where you have what we have in microcontroller. Let's consider the round robin version. So just to have a very simple idea, so round robin or control loop. Then we want to increase the number of tasks in this cooperative loop. So we are just inserting another functions in the control loop, and then it's running. So of course the control loop will circulate slower because there is additional time necessary for this extra tasks to be executed. Of course, we need a bit more memory because those extra tasks need extra memory, but the difference is tiny. In case of FPGAs, what's really problematic in real applications, from practical point of view again, is that a change of a data tape is sometimes causing our application to be twice or thrice as large as before. Yeah, that's really it. So it's in FPGA, in microcontroller, changing from int16 to int32 costs almost nothing. Of course, it costs nanoseconds in execution time, but in case of resources and this kind of stuff, it costs a tiny, so fraction of a percent of the total memory, for example, size. Here, it's really this kind of a problem. And of course, small change in an algorithm may really damage the whole idea of a program. So that small change in one place that completely influences and changes the behavior of our code. It's even worse. So consider you want to have test outputs. So you want to test some pins. So in microcontrollers, we're doing this kind of debugging with, we have a pin, we have an LED, and we want, for example, to blink the LED when something happens internally. So this kind of debugging, so that we don't connect a debugger, but rather we are using an LED. So this kind of debugging is possible, and we are doing it sometimes in microcontroller. And it costs us nothing. So we are putting just some port control, few nanoseconds, it's done. In case of FPGA, this kind of extra testing, where we just add some extra pin for testing, sometimes completely changes the behavior of our algorithm. From hardware point of view, logically, it's of course fine, but this hardware layer, in case of FPGAs, is tricky. So it may happen that causes a problem sometimes. Then the third, reuse of logic resources. So that's very much connected with the previous one. Excellent for lower performance functions. Why? Because in case of the microcontrollers, we've got sequential execution. We have mostly sequential execution. And then, of course, if we need more tasks to be performed, then the tasks are executed sequentially, and they are executed slower. So the control loop circulates, the control loop period is longer, in other words. Yeah, there is, although an important exception to this, about this in a moment. Performance, that's exactly this feature. Of course, this is the negative feature for the microcontroller, positive feature for the FPGA, so that the performance degrades when the complexity increases. And very much connected, so this feature already mentioned, a slower response to simultaneous inputs. And that's one of the major disadvantages of the microcontroller comparing to FPGA. And in many situations, it's a basic main use case for an FPGA against the use of microcontroller. Simultaneous input, simultaneous response to many inputs. In case of microcontroller, we've got a single core usually, so that's what we have in microcontrollers. That has to process an event coming from one direction and do something with this event. If we have multiple inputs and multiple events, multiple data paths, for example, because it's about event, but it's also about processing a data path, for example, filtering a data stream. In microcontroller, it's done. It's not done at the same time, so it's done sequentially, not simultaneously, but sequentially. In case of FPGA, that's the difference. One of the important differences in FPGA, one of the major advantage, really is this one that if you want to process 10 data streams at the same time, here we go. If you want to process 100 data streams or 1,000 even pins at the same time, signals coming from 1,000 pins at the same time, no problem. Of course, with 1,000 pins, you need to take appropriately large FPGA, but still it's possible. So as you can see, so here, then what's the answer to this question? Which is better? So microcontroller is better, and when? And FPGA is better, and when? In general, we could simplify everything to this, that FPGAs we are using in situations, first of all, usually where we need to process simultaneously many inputs. So many means more than 2, 3, 4, 5, 10, 20. So if we need to process really a lot of signals, a lot of input signals, and we need to get something from those signals, that's the place where the FPGA is better, where the FPGA has an edge over the microcontroller. Another advantage in case of an FPGA coming from exactly from this sequential execution is that in microcontroller we've got arithmetic logic unit. We can have a multiplier on board. We can have Mach unit as well. We can even have superscalar pipeline like in Cortex M7, so which means that a couple of things are happening at the same time. But these are just a couple of things. In case of FPGA, and that's the advantage of FPGA over the microcontroller, is that if we need a maximum speed, then we sacrifice the resources and we make the parallel implementation of an algorithm. Quite often in FPGAs, for many algorithms, when implementing them, we have a choice that we can either choose that it's gonna be very small, so the topologically small element, small piece of logic will be generated, yet, for example, 10 clock cycles will be necessary in order to process some data, so to deliver some output. But then we can modify and take more resources, so generate something larger, but at the same time process the data even asynchronously, so even at the cost of only propagation time, without even any clock cycles. So that's possible in FPGA, this kind of trade-off. That's not possible in microcontrollers. In microcontrollers, we have to stick to the instructions, we have to stick to the capabilities of the microcontrollers. And these are two major use cases for the FPGAs. If your application goes beyond those two major use cases, you should think 2 or 3 times if that's really a good idea to go into the FPGA. That's the case. That's the case today. That's the state of technology. Because today the microcontrollers are really very We have a lot of them. They are power efficient because it's not mentioned here. There should be mentioned the power efficiency. Because there is a significant difference between the microcontroller and the FPGA. The problem with FPGAs is that we have, even if we optimize our algorithm, then usually we are eating up just part of the whole FPGA chip, 20%, 30, 50, maybe 60%. It's very difficult to utilize 100% of the FPGA resources. It's almost not possible. So usually up to 70, 80% is possible. Then the router tells us that it's not possible to route the design in the FPGA, which means that we have some resources which are non-used, which are non-used and which are just eating up the power. So something that we really so that's a pure power loss. So microcontrollers are here always better. So power efficiency. So they are cheaper, they are better, they are smaller. They are slower because of the sequential execution, but there is but, and that's why the asterisk is here. Because sequential execution, of course, if we have the algorithms, the calculation algorithms, we have single core, even with superscalar pipeline, but still it's a single core, so the execution is mostly either completely sequential or mostly sequential. That's true. So that's worse than in FPGA. Okay, but in case of embedded systems and microcontrollers, processor is just one part of the whole of all the resources necessary for the embedded system to run. There are, of course, a lot of peripherals there. There are a lot of peripherals, and those peripherals are actually nothing else as delivering us kind of parallel execution of our application. So it's not about algorithm, but all in all, the embedded systems like very much this resources and the parallel operation of all the resources together with the microcontroller, which again is a very strong factor behind very strong advantage of microcontrollers compared to the FPGAs. In FPGAs, of course, we can do the same, but microcontrollers are cheaper and it's already done, it's already present. So summing up, when to use FPGA, when to use a microcontroller, sometimes it's really difficult to discern. Sometimes it's really a matter of a personal preference, which should be taken to certain applications. But today, to be honest, majority of tasks, the microcontrollers are enough for the majority of tasks that we have around us in embedded systems. FPGAs, just those two very special cases. So a lot of inputs, outputs, and or outputs, and parallel calculation algorithms. So those two cases are definitely for the FPGAs, and the others are for the microcontrollers. So for example, let's take a look at the major common applications: encryption, decryptions, neural networks, artificial intelligence, digital signal processing, software radio, image processing, decoding of communication protocols, code acceleration of MATLAB Simulink, and some other neural networks and artificial intelligence, for example, can be done in FPGAs. There are constructions today supporting coprocessors and microcontrollers supporting the AI. For example, same is with digital signal processing. So the element that microcontrollers, that the FPGAs are of course excellent at. But if you don't need to process 10 channels or a 1 gigabit per second bit stream, maybe microcontroller would do that. Would do for a much lower at a much lower cost. So in every of this category, we can think about the use of microcontroller today. Although of course the FPGAs the FPGAs are here are delivering the highest performance available and the best one, and deliver us give us the most of the capabilities. How the FPGAs are constructed internally, because that's a bit different from a microcontroller point of view. You should remember the structure. So we have those configurable logic blocks with some multiplexers and this kind of things. Yet there needs to be a method to change the content of the FPGA, because in the FPGA, in case of CPLDs, PLAs, and PALs, the situation is pretty simple, because we are just to make connections connecting two lines together. So this matrix of connections. In FPGAs, the situation is way more complex, because it's not only about making the connections, about connecting two wires together. Here, it's also very much about the RAM memory, because all the lookup tables are basically RAM cells. So it's very much about the RAM technology. Probably for this reason, the major tape of FPGA chips that we have on the market today are the SRAM tapes, FPGAs, where the lookup tables and the block RAMs, all this is RAM and nothing else, but also the connections are made based on the RAM cells. That's not a problem, because we are just Hello, welcome back. Something happened with my Zoom. I needed to restart my computer. Sorry about this. Strange thing because it's everything stopped. Okay. So once again, about the construction. So we have this SRAM based, which require, that's where we finished, as far as I remember. So we've got the situations where there is the FPGA and there is necessary a RAM tape, a RAM close to this. So not RAM, sorry. Of course, it's a non-volatile RAM, which is usually it's a flash memory usually, but it can be a microcontroller, for example. Moments, technical problems. Okay, anyway. So there is a flash here. That's not very convenient, but that's the way it is. So that we need this extra memory. So in microcontrollers we don't have it, so we have it on board. In FPGAs, it's also possible to have it integrated. These are so-called flash-based devices. So they are such devices on the market produced by some manufacturers, or the so-called anti-fuse technology. But they are those type of devices are minority. So the majority of devices that we have today on the market available are requiring are the SRAM based devices requiring external non-volatile memory. In case of the other technologies, so the anti-fuse and the flash technologies, they are in general more expensive. So they have some positive and negative features, but maybe that's not so important for us. So you can always read the presentation offline to see this basic features. In case of the FPGA inside, we've got kind of this structure where there is the major element is a configurable logic block, of course, with some connections over the interconnection matrix to various IOP blocks. Additionally, we've got extra features like DCM, like block RAM, like DSP unit, like the transceivers, serializer transceivers. So a couple of things, extra clocking subsystem as well. A couple of things extra are here. And our task during the design process is to make all the connections, forming a circuit that we need, forming the algorithm that will process the data according to our needs. So this is not such a simple task, considering this bare logic that we've got in CLBs, and the number of combinations that are available, that are possible. So here you can see the CLB block structure in Virtex 4, in Virtex 5, the CLB got more complex, but still during our hardware description, we need to utilize this kind of CLBs. Fortunately, usually we don't need to get to the level of single multiplexers and single flip-flops. The FPGAs in general are large, very large or gigantic. I'd even say this way. Here is an example of one of the FPGA family, medium-sized family, in fact. And this medium-sized family, we talk about tens of thousands of CLB blocks. Of course, each CLB block is composed of those lookup tables and flip-flops that we mentioned already during ITM course. These extra features are also existing in great numbers. So, for example, the calculation blocks, extra calculation blocks, so these are called DSP slices. We talk about hundreds or even thousands of units today, plus megabits or even megabytes of block RAMs, plenty clocking subsystems, but plenty clocking blocks. There can be hardware microprocessor even in the logic structure, and the transceivers, plenty of very fast transceivers. That's also a discerning feature from a microcontroller, by the way. Those transceivers, because there is no microprocessor and microcontroller market capable of receiving gigabits per second, single gigabits per second even. It's about megabits, tens of megabits per second. That's okay, but single or tens or hundreds of gigabits per second, forget about it in microcontrollers. And that's the feature that exists in FPGA and really works, so that we can have various kinds of serial transceivers, giving us a chance to process very fast, extremely fast bit streams coming from various directions even. Very characteristic feature of the FPGA is as well the size, so that we've got hundreds, sometimes more than 1,000 of pins that we can connect. But that's, again, we mentioned already that one of the important use cases is the situations where we need to either process signals coming from tens of inputs, or the output being or the tens of outputs needs to be driven, or hundreds maybe. So that's why so many IO pins. The lookup table, we're talking about it. The major logic standards which are supported by the FPGAs today are those ones that you can find in the market. So mainly LVTTL, LVCMOS. Sometimes there is a support for ECL, but only sometimes. But there is important thing, there is a support of the differential standards. That's also an extra feature comparing to a microcontroller, and one of those features that sometimes are make or break, or give us a chance to make a decision of choosing the FPGA against the microcontroller. So the differential lines, either receiving signals from differential lines or transmitting signals to differential over differential lines. In case of microcontroller, we can do this as well. So we can connect to the differential world, but we need to use extra chipsets, extra chips, like in CAN case, where there is a translation going on between the serial input output and parallel input output. In case of the FPGAs, we have it on board, so it's only about configuring the inputs or outputs, and we can use a differential LVDS, LVPCL, PCML. All this is in range. So besides the standard logic, the standard single-ended logic, we've got also a differential connection. In case of comparison of FPGA and ASIC, we did talk about it a year ago, because in general, what an ASIC is, ASIC is a chip which is application specific. So this is a broad category of application specific IC. If we can even think about classifying to application specific IC, a microcontroller with a program, secured program code, because we can today take a microcontroller, upload a code, and then make it secure so that it's not possible to read back the code, and it's not possible to modify the code. Such options we have today, and we could treat such a microcontroller as the ASIC as well, as the application specific IC. So some people treat it this way, although I think that better classification is that the ASIC is when we have the chip that is produced, manufactured physically in a fab somewhere, probably in the middle, in the Far East, and manufactured and tailored to our needs. So that this kind of chip is for me an ASIC. The FPGA then, because it's reprogrammable, because we can we can change it on the fly. In fact, sometimes we can have a partial reconfiguration even available. So which means that we can partially reprogram it for to deliver some new functionality or different functionality. So the FPGA then goes as a competition to ASIC. Competition which is programmable, which is cheaper in single unit, but of course not so power efficient, more expensive, and not as fast or slower than the ASIC. So we did mention about it. We did mention about it already last year, so we'll not be repeating it today. Yet the FPGA, the FPGA, there is a problem in general. In many cases, that the microcontrollers take over or eat up the FPGA world. So in places where the FPGAs were the masters 10 years ago, today everybody is using the microcontroller. So are the FPGA that? No, they aren't. They aren't that because, of course, if the microcontrollers are eating up their realm, their world, where the FPGAs were present, but the FPGAs are moving to another world, and they are taking another positions where they are still unbeatable. What are those positions? So what options do we have today in case of FPGA? After a short break. So let's meet in 10 minutes back. Let's have a short break then. Okay, welcome back. So, what are the FPGAs today? First of all, they grow. The first thing. So the classic programmable planes, programmable logic, they grow very much. So we've got, usually if you want to build your project upon a programmable logic, then you have the small ones. The small ones are, sorry. These are those ones. Then even the small ones are having quite a lot of resources. So for example, take a look about the numbers, how many DSP slices you can get, and the transceivers are quite often present, and as well the sizes are not the smallest one. So yeah, forget to make a battery operation based on the FPGA. So even the small size, and of course the large one, significantly larger with the transceivers, tens of gigabits per second, a lot of things. The price quite high, but still, that's the way it is. That's the way FPGAs are working today. Of course, the DSP slices, so all the elements are growing as well. So everything started in case of DSP slices with simple multiplier. Today it's a multiplier plus pre-adder plus the accumulator, 48-bit accumulator. So all this just as a calculation slide, with optional pipelining, arithmetic logic unit. So really plenty of things which started really with a very, very simple hardware multiplier in order to facilitate the multiplication operation, then multiply and accumulate. And today it's I wouldn't say it's a microcontroller because it isn't, but it's a very strong coprocessor, and we've got thousands of such coprocessors in one FPGA. So that's the power, that's the beauty. In case of transceivers, why do we need the transceivers? First of all, from practical point of view, we need the transceivers in the applications with very fast ADC converters. That's what I mean by very fast ADC converters. Consider the 500 megasamples, for example, per second, 12-bit samples, or maybe 8-bit samples. Still, it's going up to 4 gigabits per second, at least, so netto data transfer, and that's the place where there is a special interface which is used between such fast ADC converters and the embedded system. So this is JESD 204. There is a special interface requiring, in fact, at least single couple of 3 gigabit line. Usually 2-3 lines are used in an ADC converter. Of course, one problem is to receive such data. Second problem is to process such an amount of data. So no microcontroller on the market is capable of handling it, just an FPGA. Additionally, the FPGAs are, and that's why the transceivers, because you can interface then a microcontroller to, for example, a SATA disk drive or some other serial data transfer. So then you put a microcontroller with some slower interface, maybe parallel interface, and the FPGA then can, with this kind of transceivers, can be used to deliver a translation between, for example, hard disk drive and your embedded system. So that's also a possibility of using an FPGA in an embedded system today. Additionally, in case of those gigabit transceivers, the standard use case for those transceivers is to deliver data to the transfer lines. We can buy today. We can make optical links, for example, single lane, point-to-point optical links used quite extensively, for example, in FTTH technology, in GPON technology, the passive optical network technologies that are used in residential buildings for delivering very fast gigabit per second data transfer to final user. But yeah, the user gets 1 gigabit per second, but the hub has to deliver much more. And then that's the place where the FPGA takes its, again, an important area today. So delivering this kind of very fast throughput, splitting it, routing it, maybe the reframing the data, because there are a couple of options possible, adding some television, let's say, whatever, television stream. So all this is possible because in FPGA we've got the transceivers working at really excellent speed. So 28 gigabit per second is really top notch, but it costs quite a lot. But even 6 gigabit per second, which is a cheap version of transceiver, it costs more than a penny, or more than a cent, of course, but it's still pretty affordable. And 6 gigabit per second, no microcontroller can handle it. FPGA, yes, it does. Yes, it can. Yeah, we can use for example, the PCI Express. There are special blocks. We can use Ethernet as well, directly, gigabit Ethernet directly 10 gigabit Ethernet, for example. So when you take FPGA, you take the SFP or SFP plus module, and then you connect everything, and you have a light fast link with gigabit per second, real gigabit per second on the link. So that's possible. That's possible. Today in microcontrollers, we've got sometimes as well. We've got sometimes the onboard ADC converters. They are not very accurate. They are just like we have in microcontrollers, but that's also a response of the manufacturers of FPGAs to microcontrollers. You know, the strong part of microcontrollers, as we mentioned, are the peripherals. They're parallel operations. Of course, we can add peripherals in FPGA as well, so that's possible. Why not? But the analog peripherals. The analog peripherals needs extra electronics, which is not normally present in FPGA, and the microcontrollers were beating the FPGAs because of this. So then, since a few years, you can find more and more FPGAs on the market with ADC converter on board, so that you can integrate the ADC, treat it as a peripheral, and then it's almost on pair. It's almost the same like a microcontroller. Of course, it's not completely the same, because the microcontrollers today, for example, we've got more. We've got op-amps, we've got DACs, we've got faster ADCs than this one. So like 10 megasamples per second, or 16-bit, or differential input. Yeah, we have. But still, the basic measurements, this ADC is good enough, and this helps us to make a single chip solution, so that we don't need a single chip by the external flash, which is usually the case, but we don't need then an extra ADC chip, for example, for interfacing between the microcontroller, the analog world, and a digital FPGA. Of course, in the second direction, outputting the data, we don't have a DAC, but as a DAC, we are using PWM. So PWMs, of course, we can generate. So any number of PWMs we can generate directly from the FPGA. So that's not a problem. And then we come to, because this is the standard programmable plane, so standard FPGA. So that's the state of the art today. So very fast, very large, many number of sophisticated DSP blocks, plus fast transceivers, plus extra ADCs, and of course large memory and this kind of things. So that's about standard. That's about standard FPGAs. But that's not all that we can get today in this area. Second, quite interesting solution, I would say even very interesting solution that we can have today is a combo of a microcontroller, a physical one, and an FPGA. So a combination where there is a programmable plane, but there is also a fixed microcontroller. The fixed microcontroller for simplicity, the fixed microcontroller for the better control applications, and the programmable plane for the parallel operations for multiple input outputs and for very fast data transfer with the transceivers. In case of, so there are various names for this kind of combinations. So when the Xilinx, which is one of the manufacturers of those kind of systems, when they started to introduce it to the market, there was the name of EPP, so extensive processing platforms. But also there is such a name as HPS, so hardware processing system, various kinds of options. In general, the idea of integrating a microcontroller within the programmable plane is not new. So here it's written that it's a new class of product because there is a new name of thing. Previously, this hardware processing subsystem was simply a part, like a memory, like a DSP, a part like a clocking. So there was a CPU subsystem, a microcontroller. Today, so they just changed the name and said that it's a new class of product. But again, the idea is pretty similar that it used to be. What changed really, and that for this reason, this EPP or this thing is a bit of a new product, is that there is a change of paradigm, because instead of having a programmable plane with some hardware processing system, from this family, they started to, so the device is basically a microprocessor, a microcontroller with programmable plane, with a lot of programmable logic. So change of view, slight change of view, as you can see. So from being a programmable logic with some extra hardware processing system, we go to have processing system with extra programmable logic. So everything became processor-centric, and we call it a processor-centric architecture, which offers really flexibility and scalability of an FPGA combined with performance of ASIC chips, and power and ease of use of ASSPs. Today on board, we've got usually Cortex processors as a hardware processing subsystem, although the Intel is experimenting with something on their own. But in Xilinx constructions, the cores are Cortex cores, so A9, A15s cores, which are present inside. The applications of this kind of chipsets, the very important application today, ADAS, so driver assistance. So I know this autonomous cars, autonomous autos, and the needs of fusing signals from many sensors around and making decisions based on those sensors, and of course driving many objects based on this decision made. All this integrated into single chip solution. So that's the beauty of this single chip solution, that we can do it. So driver assistance, of course, consumer equipment, of course, factory automation, medical imaging here as well, where we have where we need to process to rapidly modify the algorithms or frequently modify the algorithms of processing an image, and again making some decisions based on this image. Military radios, broadcast cameras, and of course various kind of communication, wireless and wired. Internally, it looks more or less like this one, so that we have a Cortex-A core. On this Cortex-A core, we have add-ons, so peripherals in general. So in fact we have a microcontroller based on the application core, on the application processor, because the Cortex-A is an application processor, but we've got kind of a microcontroller with the peripherals we know from the microcontroller world, like the SPI, like I2C, like UART, like basic GPIOs. And to this, we have connected the programmable plane with standard features that were mentioned before, with the CLBs, with block RAMs, with clocking subsystem, and many other, with PCI Express blocks, with this XADC. Take a look here. So XADC. So all this combined together, and naturally the programmable logic here, first of all, works as an interface between the processing subsystem and those extra elements like the fast transceivers or the calculation blocks, so like the DSP blocks or the external ADC. But as the second option, in programmable logic, we can make blocks which will do the calculation exactly as we need it. So an example, medical imaging, and we need to we need to build, we need to process an image and look for certain features in this picture, and we develop an algorithm that will do it. So instead of implementing it laboriously inside the core, which is fast, of course, but fast and with some vector instructions, but it's not as fast as the programmable plane, as the programmable logic. A comparison, by the way, just recently, one of diploma students did a comparison of an audio algorithm, one of the audio algorithms on Cortex-A7 and on the programmable plane. And the programmable plane was twice as fast, almost 3 times as fast. So, of course, its development is more time consuming, but the final effect is very encouraging, or it shows that there is an advantage, a clear advantage of the programmable plane, even over the Cortex-A with vector unit, so with SIMD unit. Same audio algorithm. In video processing, in graphics processing, the programmable logic will have even greater advantage over the standard microcontroller. Yeah, so GPU, of course, will make a difference here, but we are talking about microcontroller comparison with the FPGA. So that's how it is. So we have in case of this thing, we've got today the family grew immensely. I would say this way. The family grew immensely because the origins were the basic things, Series 7000 with dual A9 core. So everything began with this basic family with the Artix programmable logic plane, so the smallest one. Then it evolved in various directions. So you can have the small one, single core ARM with small Artix plane, but you can go to the beast, like for example this one, where we have the A53 Cortex quad Cortex cores plus 2 R5 cores plus 2 general GPU cores on board. Oh, even here we have even video codec on board. So even such cases, even such versions are possible. Of course, there is a programmable plane here as well, pretty large programmable plane because it's a ultra scale plus. So that's this is the path of those chips. Interestingly, this small one, the smallest one, so think 7000S family, is really pretty tiny outside comparing to, of course, the chips, the Virtexes from the classic families or the chips here and here. The smallest one, so the 7000S, you can buy in a BGA case, which is more or less 1 square centimeter area. For the prices as well, pretty low comparing to other FPGAs. You know that the largest FPGAs, they have with the great number of resources can cost more than $1,000 per chip. So for standard FPGA, we usually talk about single hundreds of euros even. So that's not a very high price. So it's a pretty standard router price. So those Think 7000S costing around $20, it's a difference. It's a difference. So that's very interesting. In fact, this thing is for the applications in the embedded systems where we don't need super high performance, but we need decent performance. And for example, we have a camera sensor and we want to process the stream live. Even Cortex M7 is not suitable for this kind of application. So so automatic discerning of features from a picture, so machine learning, so artificial intelligence implemented there with some neural network. No, even Cortex M7 is too weak for this. But this 7000S, why not? Why not? Why not? Here is an example of of this chip, how it's constructed internally, and we've got the fully working GPU, which means that based on this chip we can set up an operating system easily. Of course, maybe we'll not be able to play on it on some games, but that's not for this purpose. And we can, of course, then add extra features in coming from the programmable logic, extra coprocessors, speeding up the operation, both graphic on some graphics or on some demanding signals. So that's possible, and that's what's this for. Going even further, as you could see the performance. So everything is growing. Everything is growing in case of FPGA because we have this kind of a chart where the performance of processors used to grow significantly. So first with CISC processors, 22% per year on average. Then with RISC, the performance was there was a boost in performance. So through the 90s and the first years of millennium, with the clocking being raised and efficiency being increased, and then all this led to a whooping 52% per year performance increase. But then it all started to saturate, and today we've got the performance increase only marginal. In fact, take a look. So what's being improved today is mainly the efficiency, the power efficiency, but not really the performance. So we can deliver more cores to the system, but if we have a sequential application not utilizing this power processing fully, then it's of no use. So this kind of processing is maybe not close to an end, but it's pretty much saturated. And for this reason, in case of FPGAs, the idea is about delivering chips which are, from one perspective, flexible still. So that's the idea about the FPGAs from the beginning. So they are flexible in various implementation, but from the other perspective, so that they have specialized onboard features, delivering super performance. And today, the world, in case of computing engines, take a look. In fact, we have those three major elements. So we've got processing unit, so CPU. We've got the FPGA, and we've got GPU, so vector processing. So these are the methods we have today in technology. So each of the methods is better at something and worse at something else. So the scalar processing, so the CPU itself, is excellent in decision making, complex algorithms and decision making. In case of the adaptable hardware, so the FPGA, the processing of irregular data structure is excellent. Latency critical workloads, because we've got instantaneous response to multiple inputs here. And sensor fusion, again, the same reason, so that we can combine the data coming from multiple sensors, multi-dimensional sensors, we can combine them together easily. And the GPU then, we've got parallelism, various kinds of, so GPU and partly DSP as well. So we've got domain-specific parallelism, but mainly signal processing with complex math convolutions, and of course, the classic thing, video and image processing. So these are the options that we have. And the future of programmable logic chips is basically combinations of all those three things. So the CPU, the FPGA, and the vector processing, of combining them into one chip. And this kind of future solution, which is already present, but it's still under development or deployment, maybe not even development, but under deployment in the market, it is called ACAP. So Adaptive Compute Acceleration Platform. Adaptive Compute Acceleration, so adaptive acceleration platform. So it's a next step. It's the next step. So take a look at FPGA, then EPP, so extensive processing platforms, and then the ACAPs. So here we have parallel heterogeneous computation with a mix of next generation scalar engines, adaptable engines, intelligent engines in one chip. So what is the difference? Basically, it's take a look, it's an incremental increase over the things. So it's not a huge leap forward, it's just a small step. So if you compare it to CPLDs, it's a huge leap. But naturally, over the history, it's just a gradual improvement. So we've got, like in things, we've got the scalar engines and we've got the programmable plane. What is extra is this one. So these are the intelligent engines for parallel processing. These parallel processing engines are actually giving us a chance to build a DSP on top of it, build a graphical processing unit on top of it, or the feature that is very common today, adapt or implement a machine learning algorithms here. So build a neural network and offer an artificial intelligence in object recognition, especially in decision making. Additionally, we've got some extra features for communication here with direct radio frequency, with Ethernet, 100 gigabit Ethernet, and all those huge speed communication chips, communication engines. All this is here. This is the future, giving us a chance of developing applications in software that will in fact become a hardware, because that's what we have, which means that the manufacturers can deliver with this kind of ACAP chip. They can deliver common platform with functionality completely reconfigured or reconfigurable by change of software. That's the beauty of the solution. So that in this kind of applications, one platform, universal, will do the job, just about changing the software and adapting different algorithms. So the Versal, because these chips, if EPPs were things, then ACAPs are called Versal in Xilinx terminology. In Xilinx terminology, they deliver really quite a lot. So here the AI core in Versal is promised to be at least twice as fast as the high-end GPU in these applications, and many times higher, and more than an order of magnitude higher than high-end CPU doing the job that is not for it, which means the artificial intelligence processing. So that's the direction basically we're going. Where we are moving. Yeah, here is a DSP and enhancements, for example, in MIMO technology, where we need a lot of processing going on, and the Versal chip is to be five times faster than the top-notch thing with the RF on board, UltraScale Plus RF SoC on board. So high-end thing, and this difference in performance, we will see, we will see. And the natural, I would say, one of another not very natural realms of those ACAPs, of those Versal chips, is generally the ADAS subsystems. So the autonomous cars with sensor fusion in small size and small power consumption. So take a look. It used to be one HD camera in this example with 10 watt consumption, and with the ACAP it's possible to integrate the sensor fusion, from all the sensors around, plus couple of cameras, plus the radar, ultrasound, LiDAR, plus extra machine learning here, and same power envelope here, 10 watt. The pricing is of course can be different, but still clear gain here about the new technology. And then the comparison of the encrypted traffic, so the encryption life of the chip's capabilities. So the ASSPs in 60 nanometers compared to ASSPs, of course, dedicated for this kind of operations, slower than the universal chip, and not even mentioning the Zynq. So the Versal is much better. It is promised to be much better. I would put it this way, because again, the time will tell if this really is so much better than competitors. We'll see if it goes this way. Yet, future path, as you can see. So not only FPGA, and today on the market, also a combination with sequential CPU, and combination even more with vector processing unit, combining all the functionality of the computation capabilities that we have present today in the technology. That's the future. And these are the options we have when building some complex embedded systems, because I can't imagine using it in simple ones. Beside this single chip, single core Zynq, which is not that bad. Yet here a small remark about this single chip Zynq. Then of course it's simple comparing to Versals, for example, or complex multiple core Cortex chips. Yet simpler doesn't mean as simple as microcontroller. Time to market based on a microcontroller. Of the embedded systems based on the microcontroller, I think will always be shorter than time to market of a device based on an EPP. Maybe I'm mistaken, but I will be mistaken. Maybe somebody will prove otherwise, but so far nothing changes. So if you want to use a Zynq, if you want to use a Versal, then you must really be prepared for a much higher workload comparing to a microcontroller. So there is no sense of using this kind of chips unless we need all the features of those extra features delivered by the processing platforms. Yet, how to program such a programmable logic? So the programmable plane, because usually if we have a Versal, we have a separate compiler for the processing part, separate compiler for the vector part, for the GPU part, and then we've got separate synthesizer for the programmable plane, for the programmable logic. Of course, the programmable logic today is programmed in hardware description language. There are just 200 hardware description languages on the market, so this is Verilog and VHDL today. They have pros and cons of this, of course, yet they are pretty similar, and today they are used sometimes interchangeably, and sometimes together. Although we have a project and one file, one language. This is the only rule. So you can have a project where half of the files are written in Verilog, half of the files are written in VHDL, with no harm to the functioning of the device. In general, HDL and VHDL, because we have time only to touch the HDL, the VHDL during the semester. So the VHDL in general is a way of describing the operation of the system, which means that we are describing basically the behavior of the hardware. So we have always some inputs and we have always some outputs. There is no situations like we have in C that we are writing main function. We are writing main function. So here we always need to prepare inputs and outputs. So this is a so-called entity. So we always are preparing inputs and outputs, and then in the body of our code, we are filling the connections. We are making the connection between the input and the output. So in general, in FPGA programming, in VHDL programming, we always have to have some outputs and some inputs to our device. So there is no empty function. About the design flow we discussed a year ago. So this is something you should remember. The main difference between the microcontroller design flow and VHDL design flow is the number of simulations. So that we simulate, we have at least three levels of the simulation, but we can have more. Sometimes it happens. Sometimes we have extra levels here because each level delivers us different information. And besides, if we go to the bottom level, to the timing simulation here, then some informations are obscure. So if something is not working well, then we will not be able to see it clearly. That's why usually we are doing the stimulation step by step. In HDL, first we are trying the basic logic simulation, and we go through functional down to the timing, and all the simulations have to work. So next week I'll try to show you how it works, what informations can we get when simulating a circuit. As a final, we've got to create. There is a bit file with the connections, and then this bit file then can be uploaded. Then can be then it is uploaded to the chip itself. In case of the HDL, it gives us a chance to describe the functioning circuit at different levels. Maybe a bit later. At different levels. So we start with basic circuit level and logic level. Circuit level is the level of the connection of the elements of the CLBs. So in fact, so this is this kind of level. So we can try. I don't know how a human being can connect manually 50,000 logic cells. I don't know, maybe you can try. Normally, it's an extra feature that is used only for very, very special applications, but still we can do it. So we can try with some extras to configure, to play at the level of the connection, so that we can try to build a path by ourselves in the chip itself. Then we have higher level, which is a logic level. Then we're basic on gates. Then register transfer levels, when we start to play on registers. And then we've got system level, which is usually the easiest to use and the best, because on system level we stop thinking about the hardware structure, but we focus more in this kind of description. We focus more on the behavior of our circuit. We focus more on the data structures. We focus more on the data stream, on what we are processing, and not how we are processing it. So we call this kind of system level as well behavioral modeling, behavioral description. The VHDL and Verilog giving us a chance to any of those descriptions, in fact. So at any of this level. So if you want, you can really play very hard in the hardware, but if you don't like it, you can go to system level and write just make a behavioral description. So then we have this kind of operation, this kind of idea is that, so that we have high level language and we are describing just high level operations with this language. So here is some stupid operation, but we can have some, I don't know, FFT algorithm here, or some image processing algorithm here, where we focus only on the algorithm itself, and we don't play with connections. We don't play with this kind of hardware connection. So this is called, the second method is called the structural modality. So all this is possible. We can choose, sometimes we are mixing those two or those descriptions so that we obtain our effect as soon or as fast as possible. In case of the FPGA, when we started at the top level, at the system level, then still during the synthesis, our top level design, is it graphically drawn, because sometimes we can draw it graphically, or is it written as a code, has to be translated to some intermediate format, and this intermediate format is called RTL. So we start from graphics, normally graphical description or the description in VHDL or Verilog. Then it is translated to some RTL, which is then optimized. RTL is a combination of gates and registers. Depending on the need, then there's an optimization, automatic optimization. We don't need to do it, fortunately, on our own. And only after the optimization that starts this placing, mapping, and routing. So here starts placing, mapping, and routing, and then we've got the final bit file that we can upload to our chip. That's how the synthesis works in general in VHDL. So we start with the high-level language, with high-level structures, with some pointers, even some functions, but we end up with a plain binary file. And then we should start to view the basic constructs of the VHDL, but we'll try to do it more on some examples, and this we'll do already next week. So next week we'll try to, unfortunately remotely, but we'll try to play a bit with it. A small question to you, because remotely it means that you are sitting whole day remotely, right? So that you are not able to come to the university on Thursday. Because I'm thinking, to be honest, I'm thinking about using a lab. I'm not sure if it is free, but I can check about using 142 lab, so that you'll be able to follow me in case of simple program creation and simple simulation, because it might be much more interesting than just listening to this and viewing and seeing it as kind of a film. But the question is, are you able to come next Thursday to the university? That's the first question, because if you are not able, then it's not a question. So that's the question to you.
I think we have remote exams the next Thursday.
Okay. So then, not an issue then. So if you have remote exams, then it's not an issue. So unfortunately, we will have to do it remotely. Thank you very much then for your attention, and see you next week.